So good evening. Uh, Today we are on the third day of our ongoing online lecture series on emerging technologies. Just 1 minute. Where we will hear actually a discussion on one of the most important topic, artificial intelligence, from one of the expert in this field, Dr. Saptarshi Mukherjee, my beloved Saptarshi. Just before that, I just introduced Dr. Goswami. He's an assistant professor and head of the computer science at Bangladeshi Morning College. He is a founding member of the data science lab at the University of Calcutta, where he serves as a senior research scientist and PhD supervisor with over a decade of industry experience in leading IT firms before transitioning into the academia. He has significantly contributed to research, earning an H index of 20, over 2,000 citations on Google Scholar. He is the author of best-selling textbooks on deep learning and AI, published by the Pearson India. Beyond academia, he has served as the advisory roles for government departments in West Bengal, including IT and higher education, and is actively involved in the Center of Excellence on AI. Dr. Goswami is an executive member of the Society for Data Science and lead organizer of the ICDMI conference series. He has also briefly worked as a visiting scientist at Iowa Prefectural University, Japan. His YouTube lectures on the machine learning are featured in the National Digital Library of India, further extending his impact on the AI education and research. I am lucky that I have the opportunity to work with him for last 5 years. Today, I am sure that you will enjoy this discussion very much. You know that I actually briefly summarize the topics that I talk about at the beginning of each discussion. Like, first of all, you will actually turn off your mobile, microphone, and camera. And all the lectures of this lecture series actually are being uploaded to our YouTube channel, Online MAKAUT. So I request all of you to subscribe the channel. And at the end of this session, there will be a question answer session. And you can ask the question. If you want to ask, then you raise your hand and I will select accordingly. Okay. So now I request Saptarshi to start his session. Meanwhile, a lot of people are waiting, and so I actually admit all. And Saptarshi, I request you to start the session. Saptarshi, please.
Yes. So thank you so much, Pritimoy, for such a lovely, introduction and such warm welcome. Those of you who know Pritimoy, he's a technical wizard himself, doing a lot of research in different form and shape, right? So very recently, one of his books on AI has been published by Government of West Bengal. So it really feels great to be introduced by him. And of course, we go a long way, sharing some of the responsibilities of the software systems of the state, especially higher education department. We are around 7:15, and as Pritimoy pointed out, we'll have some question and answer session. So it's a Saturday evening, and I thank each one of you. I can see that around 60 participants have joined. So I thank each one of you for taking time out from your personal time. Today is a very important day from marketing and commercialization. This being touted as Valentine's Day, right? So I hope that we have not jeopardized many of your plans. But the age probably we are in, right? So we have to seriously think that if AI should be our Valentine. Okay. So with that note, let me bring up my PPT. So I have, quite a lot of content, but we'll skim through where it is required. And you can understand that probably in one session we cannot cover each aspect of AI. And AI has really evolved, last after this Chat GPT explosion, right? Drop of Chat GPT, right? So every theory, you need to take a look in a different manner altogether. Okay, so it will probably not be possible to look at all the nuances, but I will surely touch upon some of the important things, right? As example, I will probably spend good time on neural networks. I'll spend good time on language AI, and maybe if we get time, we may talk about agents and all these things, right? Okay, so let me, without further ado, present my screen. I hope this is visible.
Yes,
Yeah,
yes.
I
Visible.
yeah, I can see myself. That's good. Right. So this has been already very nicely articulated by Prithima, but this is just at one place. Okay. Regarding my background, other roles, and community initiatives, so all have been covered. Uh, as it will be part of the YouTube, and this lecture would be archived. So I thought I'll put a slide around that. Okay, so these two books are uh, from Pearson, one on deep learning and another is for AI for everyone. And probably there is going to be one more. So we are already in agreement with Pearson on another book title on generative and agentic AI. But again, uh, as you see that the TOC, the table of content, is continuously getting changed. Okay. All right. So what I want to start discussing with is, or how I have thought of uh, breaking down the different sections is forward of AI. So some of the histories or some of the definitions of AI. Okay, some of the divisions of AI. And then we'll move to neural networks, right? Because this discipline or this section of the AI is now most popular, being used everywhere, right? Getting most of the attention, And then I will talk very little about computer vision. And finally, I'll move to language AI. So probably I would like to spend maybe 30-40% of the time of mine in language AI, right? But let's see how it pans out, how much time we take covering, each of the sections, right? And this is one of the slides I typically use to start with any new AI lectures, right? And the question I would ask participants is that which face looks real, yeah, right? Is it A, is it B, or is it C? And it's a trick question, okay, because all these three are not face of real people. So there is a very, very nice study where people have shown that from 2014, right, how AI generated images have become more realistic. Okay, probably I can share reference later. And so that was about images, and then you can read this text, okay, accompanying with an image, right? ভোরের আলো জানলার কাঁচ ছুঁয়ে ঘরে ঢোকে, ঘুম ভাঙে পাখির ডাকে, চারপাশে এক অদ্ভুত নীরবতা, যেন শহর এখনো পুরো জেগে ওঠেনি. So I don't know how you will find it, but you again probably can understand that this is not written by any human being. Okay, so this is also generated by AI. Okay, so having said that, right? So this is what we call as generative AI, right? So what is generative AI? Again, I like these are very high level definitions, okay, and then we can look at the detail. So essentially, it is an AI program which can generate, right? And so if I say that it generates, the obvious follow-up question is generate what? Okay, so it can generate any media. So it can be text, it can be images, it can be video, it can be audio, or it can be a combination of it, which we call as the multimodal form of generation. Okay, and generate like whom? So here, that concept of Turing test comes, right? So the generation should be human-like, right? So if it is gibberish, if it doesn't make sense, then probably the fun of generating or making it useful, that will go. Okay. So, however, there are a lot of memes that go around where people have now started equating this set of generative AI, right? So the Chat GPT series of family, right? The generative pre-transformers, that they are the AI. Yeah. So, but if you think very clearly, you see that typically this generative AI is based on transformer architectures. Transformer architectures are essentially a part of deep learning. Okay, deep learning is all about efficient neural network architectures. Okay, and generative AI is a subset of that. Okay, and if you see, in turn, deep learning is a part of machine learning, and finally, machine learning is part of artificial intelligence. So we had a lot of, I'll just try to give some example. So we had a lot of learning algorithms, right? As example, we have support vector machine, or we have random forest, right? Or we have boosting algorithms. Okay, so even like clustering algorithms. So all these are part of machine learning. Okay, the neural network based algorithms, we call them part of deep learning. And then some very specialized architecture, very specialized deep architectures with a lot of parameters, right? So there where generative AI sets in. Okay, and all these things actually comes under artificial intelligence. Again, artificial intelligence, if you see, you have many other things. As example, you have one point of time there was a lot of research going on nature inspired algorithms. So one of them being genetic algorithm or particle swarm optimization, right? So all these actually are part of artificial intelligence. Okay, and then you also have the series of state space search, right? So you have the basic hill climbing and simulated annealing. So those are there. You have all this modeling of uncertainty in terms of fuzzy and rough set, right? So those are also part of artificial intelligence, right? So this is a very tunnel view. If we think that generative AI is what is AI, okay, but I will be very upfront. I see it in some of the BOSs, and I discuss with a lot of people in the industry or my colleagues who are in such positions. So a trend that we see now is even you pick up some of the courses from like top institutes, you will see that a lot of AI content or the syllabus of AI has been focusing more on this neural networks and transformers and generative AI and so on and so forth. Okay, and the recent favorite being agentic AI. Okay, so let's go ahead. Right. So here is a very quick, very quick, outline of how this AI thing or the AI term came into place. Like I call it the history. Right. So this came in the year 1956, the famous Dartmouth conference, and the main person who was responsible, okay, was John McCarthy. Okay, probably at that point of time he was a very young and energetic assistant professor of age 28 or 29, right? And he convinced 9 other people to come and join a conference to discuss about AI. Okay, and there are many stories that go around. Okay, that artificial intelligence was not a very automatic choice to describe the term. Okay, so people were in two minds, right? That what could be some other names, but then it was AI for some reason. Okay, and people were not very. So I mean, you think about it, right? So we don't typically, if we associate artificial with something, uh, I mean, it is not probably very lucrative, right? But it doesn't create a very swaggy impression. Okay, so but yes, that's how artificial intelligence came into picture. And you look at the people here. Okay, so some of you, I'm sure you can identify as example Marvin Minsky or Claude Shannon or Arthur Samuel or Herbert Simon. So they were, like AI rock stars in their own right. Okay, Herbert Simon, in fact, got Nobel Prize for his contribution in economics. Okay, so and I'll again share something funny. So you may be seeing all over social media and LinkedIn and everywhere that next week you have the AI Impact Summit going to happen in Delhi, and a lot of big peoples are kind of coming, right? So I could see that there is a speech by Bill Gates, there is a speech by Sundar Pichai, there is a speech by Jan LeCun. Okay, so all these big who's who are coming and attending this Impact Summit, and probably all the big corporates have jumped in to sponsor and be part of this journey. Okay, and right, so when this AI was being conceived, right? So 1956 conference that I'm talking about, right? So they actually are not getting funding to organize this conference. Okay, and finally Rockefeller came in, and 50% of the conference was actually funded. Okay, this is just a tidbit. Okay, so what is AI? Okay, so we'll try to define it many ways later on, right? But here is a very practical, usable, very practical, usable definition. It goes like this: that if a machine can perform intelligent activities, then we say the machine has artificial intelligence. Okay. Uh, Again, I mean, you can ask that, okay, what do you mean by intelligent activities, right? Because this is quite subjective, right? However, so again, I mean, a more expanded version is that if some behavior, right, if performed by human, is considered as intelligent, and if a machine can do that activity, right, so then it is called as artificial intelligence. Okay, so here this is a kind of a definition that is more practical. Okay, and if we look at AI approaches, so these I have discussed earlier also, right? So AI approaches can be one way, divided into two things, right? So one is deductive AI, and another is inductive AI. Okay, so you know the meaning of deductive, right? So you deduce something, right? So there are some rules given, some facts given, and on the basis of that you conclude something. Okay, and what is inductive AI? So inductive AI, as you know, that you are learning by induction. So probably there are some examples, right, by which you are learning. So I'll try to give a very quick analogy. So let's say you are reading or you are trying to grasp a maths chapter. Okay, and so one of the ways that actually you go through different set of algorithms, right, or sorry, different set of theories, and you try to use the theory, the corollaries, and try to use it for problems. Okay, so this is one way. Okay, but funnily, I don't know for you, but something worked for me is that I used to learn from examples. So you can see from the examples that what are the different steps, how will you start, how will form the middle steps, and how you will take that to solution. Okay, so inductive is that way, not going by the theory, but learning the theory from the examples. Okay, so you can think of machine learning as as a part of inductive AI, and then deep learning to be a part of machine learning, which we already discussed, right? So you might ask me that, okay, then do we not have any success on the deductive AI side? Actually, when AI started its journey, right, it was all about deductive AI. Okay, so we had something called as rule-based systems, okay, or expert systems, where uh, there was a lot of use of deductive AI, or I will say that that was an example of deductive AI. Okay, so 1970s, 80s, when people were working on production grade AI systems, so they were essentially mostly deductive AI based systems. Okay, but people realized that deductive AI has some issues and limitations. Okay, so then where the surge in inductive AI came in, so we also have a timeline-wise journey of AI, where we will talk about different milestones that spans across this journey of AI. Okay, so yes, this is an example, a very famous example, which you call a syllogism, right? Which is deductive AI, that all canine animals have 4 legs. All dogs are canines. Therefore, dogs have 4 legs. Okay, so there are some facts, and from that facts, you are making some inference. Okay, or you are deducing something. Okay, all right. And example of inductive AI is that I saw a couple of dogs yesterday. Right, both had 4 legs. Therefore, all dogs have 4 legs. Okay, so it's based on what I have seen, right? Based on my knowledge. Okay, so this is what the inductive set says. And then AI methods also can be bifurcated into symbolic AI and sub-symbolic AI. Okay, so what is the meaning of this? It's very simple, right? So it turns out that there are many things that we do, okay, which you cannot express in terms of symbols. Okay, so I will give you some examples. So let's say that you have a very complex calculation by which you are trying to see that what part of a medical claim will be covered by a insurance company, right? And that can be as complicated as a road accident where multiple parties are involved. They have like different level of liability sharing and so on and so forth. Okay, uh, so uh, you can actually write down the logic, or you can precisely write down the logic. Okay, so you can express your logic in terms of symbols. Okay, but you know uh, if you let's say you can very easily identify a species to be a tiger. Okay, and if someone asks you that you write down, okay, you write down the logic, okay, by which I can identify it as a tiger. Okay, then you will see that will start kind of faltering. We cannot do that very properly, so we do that all the time. Okay, that we get some idea. Okay, we use some intuition, right, and we come to some conclusion. Okay, so that may not be optimal, that may not be correct, but we come to some conclusion. Okay, that suddenly if we hear a particular music, we can very clearly remember, okay, which movie that belongs from. But how how you remembered from that particular part, if someone asks you that you write down in a copy, okay, the steps by which you identified this, or essentially maybe you very easily you can identify, oh, this song was like this song was sung by great Muhammad Rafi. But if someone asks you that, okay, you tell me by explicit logic or explicit statements that why this is Muhammad Rafi, right? And then you'll see that you cannot explain. And very interestingly, very interestingly, humans work a lot with sub-symbolic AI. And neural networks are actually an example of subsymbolic AI system. Okay. Uh, so here is just following through the deductive AI thing. Okay, that it has facts and rules, right? So the one that we used was more bookish. So here there was medical expert system. So one famous medical expert system was MySyn. Okay, so where you will use their symptoms, and there will be a symptom database, there will be a medicine database, and you can suggest certain things. Okay, please excuse my eating, so I can't help it. And just give me a minute and I'll continue. Sorry about that. Okay, so you can see that you can there will be some facts, and then you will have some rules. So left hand side you have the facts, and then right hand side how you will use rules to come to an inference, right? So that is there. And this system was pretty successful, right? So there were many medical expert systems which were running at a production grade. Okay, so yeah, so a doctor can enter John's symptom in expert system and then use a chain of inference in order to conclude that an antibiotic needs to be administered to John. Okay, now of course, I mean, the point is not to engage a doctor, because then you are blocking the expert's time. Rather, it is using other experts who like not so costly as a doctor, right? Maybe nursing people who can use this system, right? Or maybe for a state like West Bengal, where there are many primary health workers, right? So this kind of systems could have been useful. Okay. And then let me also give an example of symbolic AI. So this is a classic example. Okay, so you remember this missionary and cannibal problem, right? So this is a okay. So you are given a connection with AI and puzzle is very long. Okay, so because you remember the definition. Consider some activities that, if done by a human, is considered intelligent. Then if that activity can be performed by a program, we say that program has artificial intelligence, right? So of course, solving puzzle is an intelligent activity. Okay, I think you'll agree. Or playing chess is a intelligent activity, right? So here is a puzzle where you have 3 missionaries and 3 boats on one side of the river, and you have to take them to the other side using a boat. Also a constraint that on both banks, or even in the boat, right? A boat, it is not possible. If any side of the bank, the missionaries are outnumbered by cannibals. So there are 2 cannibals in one side and one missionary on that side. Then the cannibals are going to eat the missionary, right? So your task is that to take them to the other side, and another constraint is the boat cannot cross the river by itself with no people on board. Okay, so typically, what you do in this kind of situation is you take help of state space search, right? And see, this is how we symbolize, right? So this is also a part interests me greatly, and you might find interesting also that there is a textual description of the problem. Then how you can convert that textual description in kind of a formal representation, right? So you see that, and this formal representation, please understand that it may not be like unequivocal. So you may have something, I may have another thing. That's not a problem, right? But as long as it is expressed like without ambiguity, right, then it is fine. As example, we will say that current state is left bank. So we are kind of using maybe Python leaves or maybe arrays, right? Where we are saying 3 missionaries are on the left bank, 3 cannibals on the left bank, and 1 boat on the left bank, and right bank the list is empty. Okay, and what is the desired state? Left bank is empty and right bank is 3 missionaries, 3 cannibals, and 1 boat. And then gradually what we need to do is we need to define functions, right? Which we call, we move from one state to another state, right? And then every step we check that if that is the desired state, right? So that's how, you know, state space search would work, right? So this is an example of symbolic AI. Okay, so before I move, right, so I have very few, right, very probably 3 or 4 only. Okay, so just you know, to see that you are with me. Okay, so this is a question, right? Between deductive and inductive reasoning, which one do you think humans use more in daily life? So you can write in the chat, or you know, I don't know if you can unmute yourself. And the question is, between deductive and inductive reasoning, which one do you think humans use more in daily life? So yeah, we are getting answers. Inductive. Mr. Ovirup and Mr. Rahul has replied using chat. Very good. Any other participants want to say anything? Yeah, so a lot of votes are coming from inductive. Okay, good. Yeah, so you probably realize, so that's there is a trick, right? Yeah, so more vote for inductive. Great. I hope that you are not being inductive here. You are not learning from the examples of others' responses, right? So this is what is your original thought process. Okay, jokes apart. So yes, you are absolutely right. So essentially, you know, let's say you are following, say that you see by some way you can understand that, okay, today it is going to rain, right? So then you are going to carry an umbrella, okay, or you are going to take some measures, right? So these are mostly inductive. You cannot say that how you know, looking at the cloud you essentially understood, because this is your experience, right? This is your experience, what you have seen earlier, right? From that you are you are going to some kind of an action. Okay, excellent. So many of you are saying inductive. Now the question to you is that do you think inductive AI, okay, so this is a follow-up, inductive AI will always get the correct result? Of response, so that really motivates me. Okay, so as I said, the next question is that do you think inductive AI can make some errors, right? Or can inductive AI is always correct? Okay, so you can probably try answering that. I hope you understood the question, that is inductive AI always correct? Okay, so sometime it's error. Yeah, so let me give you an example. Okay, that you actually yeah, so some people are saying yes. Okay, so mm, the thing is that, you know, that let's say you go to yeah, so anomalies, yes, so it can make error where anomalies come, black swan. Yeah, yeah, nice, very nice. Right, so yes, I mean swan is a very nice example. Okay, so it's like that you have gone somewhere, right? And so, typically, even if, like all of us, who are Bengalis, so one of our favorite activities during winter used to be that, we'll go to Alipur Zoo, right? And uh, this time of the year, there will be a lot of migratory birds that would come, right? But you'll see that a lot of cases, yes. So very, very nice responses that I'm getting, right? Experience, yeah, inactive AI is not always correct. Yeah, you are right. So basically, you will see, a lot of swans. And if you maybe have walked for 5 minutes and you have seen only white swans, right? So you inductive AI sort of methods will try concluding that swan means white, right? So this can be this can be one of the problem. Okay, so that's what probably people are trying to tell. And I also give a funny example. Okay, so let us say that we are talking, giving an example of dog having 4 legs, right? And let's say that you have actually visited a veterinary hospital. Okay, and so all the poor animals who meets an accident, right? So they are brought there and they are treated. And very, very unfortunately, there are a lot of stray dogs, okay, who has lost one of their legs, right? And maybe you have seen 2 or 3 dogs, who have lost their legs, right? And you are concluding, okay, so dogs have 3 legs, right? So what I'm trying to tell is that when we learn from examples, okay, then a lot depends on context, right? So if I look at a person, you look at you, right? Look at you, and you are in a like classroom or a research lab setting. You have a certain kind of behavior, and then you are in a movie hall with your friends, right? You are the same person, but your behavior is changing. So the context is very, very, very context is very context. Let's say your class or research lab performance. I say that, okay, uh, this guy doesn't talk too much and actually does like focuses completely on his work. However, like when you are probably have gone to enjoy a match or enjoy a movie, your behavior is completely different, right? So if we try to generalize this, that you will also be quiet when you are actually like watching a movie or enjoying a match, then it will not be correct, right? So this is where inductive AI can go wrong. Yeah. So thank you all for your responses, right? Okay. So so we have talked quite a lot about what is AI and all these things. Okay, but then if you think that artificial is actually qualifying the term intelligence. Okay, so artificial is being an adjective over here. So if we want to define AI, we also need to understand what is intelligence. Okay, so these are again some very, very generic guidelines. Okay, so some common definitions of intelligence include the ability to learn and adapt to new situation, right? So again, human beings, you put them anywhere, right? So they can adapt to new situations. They move from one job to another job, one specialization to another specialization, one department. They can learn and adapt to new situation. Okay, and then of solve problems. So solve problems may not be like theoretical problems. It can be practical problems related to our own life. Uh, okay, so this is super important. Ability to think abstractly and reason logically. So this thinking abstractly, right? So this is what makes humans human. Okay, so the way for computer science we have thought about data structures, right? Or maybe game theory, right? So all these are abstractions, right? Or I was talking about genetic algorithm, right? So when we think of the solutions, right? When we think of the solutions as chromosomes and each component of the solution as a gene, so that is actually thinking abstractly, right? The ability to understand and use of language. Okay, so yeah, this is also very, very important activity. So this is something which I was referring as, language AI, and ability to be creative and innovative, right? So these things broadly you can think of, part of being intelligent, okay? Or this is what is intelligence, okay? And Marvin Minsky, I think you have not forgotten his name. So he was one of the first 10, right? First 10 people of AI, right? So he said that he coined the phrase suitcase words. Okay, so he said that suitcase intelligence is a suitcase word with many cousins, right? So such as thinking, cognition, consciousness, emotion. So each is packed like a suitcase with a jumble of different meaning. So in a suitcase you have different things, right? So if you try to put different concepts which symbolizes big intelligence, so there are a lot of things which are going to pack in that suitcase, right? So that's what we try to tell. Okay, all right. And when we think about intelligence, we relate this, okay, to brain, right? Because a brain is the component which probably we call like different components of brain, right? Left brain, right brain, right? We talk about amygdala or many other things, right? About brains, right? So where you have the central nervous system, right? So uh, you can think of that brain is actually the organ which symbolizes intelligence in human beings, right? So I think you'll agree, right? So this is a very catchy kind of slide where the brain size of different animals are compared, okay? And you may be surprised to know that there are some animals, right, who has like higher brain size than human being. As example, dolphin has a higher brain size than human being, or even per se, some species of whales also have higher brain size. Even probably African elephant has higher brain size than human beings. However, so it's not only brain size. You will have to also look at the ratio of the brain size with their body. Okay, so okay. So what is the connection of discussion, right? So I'll come to that, right? So when people were thinking of devising or attempting to solve this puzzle of artificial intelligence, they realized that brain could hold the key, right? And we should, so one of the approaches of any system designer is that we'll start small. Okay, so we'll componentize and then we look at a small piece and we'll try to build that first, right? So what right? So this is the neural network, right? The neural network that is there. So there are around 80 to 100 billion nerve cells known as neurons. Okay, the human brain is kept. So for them, right, the human brain is capable of doing some astonishing feats, right? And then each neuron is connected to more than 1,000 other neurons. Okay, so making the total number of connection in the brains around 60 trillion, right? And then neurons are organized in patterns and networks within the brain and can communicate with each other at incredible speed, right? So people are thinking that if we can somehow build artificial brain, okay, then maybe that is what should be the grand goal of AI, right? The creating an artificial brain. And to create an artificial brain, our first stoppage would be creating an artificial neuron. Okay, so here is a very high level overview of what is a neuron, and those with biology background, don't shoot me. Okay, so this is a very high level discussion, right? Just for the purpose of modeling this, right? Like creating an abstraction for neuron. Okay, so you can think neuron to be a basic computation unit. I think that's fine. It takes input from some other neurons, okay, processes it and gives output of some other neuron. Okay, so very generic definition, and there are a lot of them which are interconnected, and together they can perform complex tasks, right? So this is how we are trying to do an abstraction, that if I need to create a artificial neuron, that should be a computation unit which should have the ability to take input from different neurons, process it somehow, and then give the output back to some other neuron. Okay, and then we'll also have to figure out that how we can interconnect them and how we can make them perform tasks. If we can solve this, if we can make this, then we have a artificial neural at our hand. Okay. So the first attempt for that was what we call as MP neuron. And essentially, this happened even before the Dartmouth conference. So this would be around 1940s. Okay, and the two gentlemen whose picture you can see on the right hand side are the ones who invented this, McCullough and Pitt, and like the initials of their name. So that gives the name MP neuron. Okay, so you see that you look at this. Okay, so this x1, x2, x3 up to xn. Okay, so these are your inputs, right? So they are annotated, subscripted like appropriately, and those values are 0 and 1. So the inputs are actually binary inputs. Okay, and there are two parts. One part we indicate as G, another part as F. Okay, and which is still holds, right? So that 1940 definition still holds. Okay, so what G tries to do is G tries to kind of aggregate the inputs. Okay, what G tries to do again, G tries to aggregate. Okay, and what F tries to do, it takes the aggregate value, and then based on the aggregate value, it has some logic to give the output as 0 and 1. But if you see both the inputs and outputs, right? So they are binary here. Okay. So this was what was MP neuron, and you might think that, okay, what good this is going to do. So let's take an example of a movie, right? So let's say you are like trying to decide whether to watch a movie or not. Okay. So if you decide to watch the movie, then the output should be 1, and if you don't decide, then the output will be 0. Okay, and then you may have different inputs. Okay, so as example, it can be about the genre, right? So is it a thriller? Again, you can make it you can make it binary. Okay, or maybe you are a Akshay Kumar fan. Okay, so one input is Akshay Kumar in the movie. So again, the input is 0 or 1. Does the movie have a 6+ IMDb rating? Again, the output is the value of the input is 0 and 1. Okay, so you can see that we are kind of trying to attempt to make it 0 or 1, right? Because first two are fine, but then does the movie have a 6+ IMDb rating? So we are kind of converting it into a binary variable, right? So ideal thing that we would have liked to do was to actually take the actual rating of IMDb, right? So it may be 5, it can be 6.1, it can be 8.9, whatever it is, right? So that would have been the ideal case. Okay, right? And what, as I said, what G does, G actually aggregates x1 to xn, and then what F does is that if that aggregated value is more than theta, which you call as threshold, right? Then it is greater than 0. Then probably we should read it then 1 else 0, not then 0 else 1. Okay, so this is what this MP neuron used to do. Okay, and it turned out, or you might think that MP neurons looks to be too simple to be useful, right? So there are a lot of limitations. It has to be 0 and 1. Okay, and we are doing some simple addition, right? So we saw over the period of time that we can use MP neurons, right, to implement basic Boolean function. Okay, so we can have the logic like that, right? Having said the logic that we can tweak the value of theta in a way that we can implement this OR logic. Okay, so what is the value of theta? So here, you can keep the value of theta as 1, right? So you will simply add 0 plus 0, right? So it is less than 1, so it is 0. and then you have 0 plus 1 is 1. So, it is greater than equal to 1. So the output will be 1, and so on and so forth. Okay. So you can implement the same using, using your OR function. Okay. And there is a very, very nice, geometrical representation also. So if you see that we can conceptualize this as x1 plus x2 equal to theta, which is 1 in this case, which is a straight line. Okay. So if anything is at the left side of the line, right, then it is 0. Or anything that is on the line and on the right hand side, then it is 1. Okay. So there was a very nice geometrical connotation also of this MP neuron. Okay. And then perceptrons came, and you see that there were some improvements. The first improvements was that the inputs now can have different weights. Okay. So why do we need different weights? So I'll just give you an example in a short while, right? And they can also have real values. Thirdly, the weight parameters are learnable. Okay, so we call that as perceptron learning algorithm. Okay, so by which we can learn the weight parameters. Okay, so when we say inputs now can have different weights, so let me try to give an example, right? So you are actually, let's say, sitting in your drawing room, okay, and you hear the sound of your calling bell. Okay, or you not, I will not say you hear the sound of your calling bell, you hear the sound of calling bell. Okay, but you don't get up. Okay, so what may be the reason? The reason may be, you can understand that that calling bell is actually of your neighbors, right? So you are not giving any weight to that input. You are receiving an input, right? Or let's say, you are hearing me, but then there may be a lot of background noise, right? So maybe a vehicle is passing you, or maybe your family members are doing their regular work, so there are some noise due to that, right? So they are also going as an input to you, but are you attending to those inputs with equal weightage? No, you are not, right? But then, like, if you hear something like, though you are putting a lot of attention to what is being discussed over here, but let's say you hear some of your family members calling for help, right? So then you'll probably leave everything and run to see what has happened. Okay, so what I'm trying to say is that in a real world scenario, there are a lot of inputs that you get, but they have different weights attached to it. Okay, so that's why weight is very important. The second important thing is that I already gave you the IMDb example. Okay, that like artificially, forcefully making them a binary variable will not take this a long way, right? So it is better that you allow real values. So that's what happened. Okay, and finally, weight parameters are learnable. So that's where the most important thing comes into play. Okay, so that's what is the perceptron learning algorithm. Okay, so where you actually look at the input and look at the output. Okay, so you think of it as some undefined function, okay, which connects input to output, and this function can be defined using this W1, W2, W3, and theta. So what you can do is, looking at some examples, you can try derive the value of W1, W2, W3, and theta, right? So this was achieved through perceptron learning algorithm. Okay, and this is where this probably inductive thinking is coming on, right? So you have some examples, and from there you are trying to figure out this W1, W2, W3, and so on and so forth. Okay, we are attempting the same problem now, that x1 is 0, x2 is 0, right? So you have W0, okay, which we call as the bias term, and then you are having Wixi, right? And this should be less than 0. And for the other cases, it should be greater than 0. Now, only thing that you see as a change is that the equation has now become inequalities because you are using using learnable values like w1 w2. Okay, and you may probably try to solve these inequalities, and you probably will get a solution zone. So in the solution zone, what will happen is that you may not get like unique solutions, right? But you will get a set of solution which actually uh, conforms to this system of equations. Okay. Uh, so again, let's say one possible solution is W0 is -1, W1 is 1.1, and W2 is 1.1. Right. So if we use something like this, again, what the geometrical connotation that I was talking about still holds. Okay. Fair enough. Right. And you have already gone through a course on or a session on machine learning, right? So I will try to quickly connect perceptron with machine learning. Okay, so you have seen that one of the important parts of machine learning is supervised learning, and then supervised learning, one of the important tasks is classification. You of course have regression also, right? And typically machine learning have two steps, right? So you have level data, right? So you have data about ducks and not ducks, right? So duck and not duck are the two classes, and then you go through a supervised learning and a supervised learning phase, and the output is a predictive model. Okay, and then when you take an unlabeled observation and you put through this predictive model or function, it predicts the label. So that's basic SOP of a supervised learning framework, okay, or algorithm, right? And typically you can think that if turnovers and like that, right? So if it is very less, right, then they are falling companies, else they are surviving companies. Okay, and so this red circles indicate one class and this green cross indicate another class. Okay, and essentially if you are trying to classify them, what you are trying to do is you are trying to draw a separating line. Okay, so you are trying to draw a separating line in a classification algorithm. To put it very simple, this line is actually called as the decision boundary. Okay, and different algorithms try to approach it in different way. I think try to approach this as that, right? So linear regression will have a simple line. Logistic regression will have a S-shaped line, right? Decision tree will allow you to have it will allow you to have like multiple lines in a decision boundary. So one line of decision boundary can be perpendicular or orthogonal to another line, right? So that's how it goes. Then you have support vector machine, okay, so which approaches it in a different way. So you are trying to draw a line, but you have the concept of hyperplane where you are trying to draw also supporting line. Okay, but this like drawing the line, okay, this is a very core philosophy of machine learning. And why we are drawing the line? We essentially want to separate one class from the another, right? So at a very, very high level. Okay. So now we just learned that perceptron also has a geometric connotation where perceptron can also kind of come to a line. Okay. So aren't we saying that perceptron can also be used for classification, right? So that's the connection with machine learning and perceptron. And of course, it is not limited to 2D. So if you have 3D data, then you can still use perceptron. Only thing is that now you are not looking for the line, but now you are looking for the plane. Okay. Here you see that there is a plane which separates these classes, and essentially as you go to more dimension, right? Then what we call them as hyperplanes. Okay. Okay, and this is something probably you may have seen here or in your earlier sessions, right? One of the overused simplifications of machine learning, that in a typical computer science program, let's say you are trying to find factorial. So you have created the program first, then you are giving an input which is like maybe 5, and then you are getting the output as 120. You are writing a factorial program. Okay, or it can be prime number or anything, right? Uh, However, in machine learning, okay, you give the data and the output, and then you get the program. So again, see the connection of inductive learning that we are talking about, right? So we are learning from example that if it is the data, if this is the input, this is the output. What is data? Data is input, right? So you are kind of learning, trying to learn this. So here you have been given like 1 1, 2 2, 3 6, 4 24, 5 120, 6 720, and so on and so forth. Okay, so essentially you might have realized that I'm picking up the number and its factorials, right? And the program actually tries to see, or writing the program, okay, which can link the input to the output. Okay, so that's what machine learning approaches. Okay, and uh, here also you'll see that symbolic and non-symbolic connection, right? So ML problems are typically not symbolic problems, right? So there are a set of problems where we know exact steps to follow, like find whether number is a prime number or not, calculating GCD of two numbers, calculating factorials. Okay, so all these are examples of problems where we exactly know the steps to be taken or followed to solve the problem. However, if we want to find out whether a particular user is going to like a movie or not, right? So that is not something where you know the exact steps, okay? Or if a person will default in load, okay? So we have drifted a little bit and just established the uh, connection of MP neuron and then perceptron with our machine learning discipline. Okay, that we are essentially trying to get the decision boundary and so on and so forth. Okay, so now I think it was 1969. Okay, and where so 1969 was a time when the symbolic AI group was dominating, right? The inductive AI was not dominating. The deductive AI group was dominating. Okay, so Minsky was proponent of this. Okay, and he with his student, I think his last surname was Papert. Minsky and Papert actually wrote a book where they posed this problem that okay, you are saying that perceptrons can solve Boolean functions. I'm not talking about very complex function and so on and so forth. And you are saying it's learnable. So can you learn, okay, the parameters W0, W1, and W2 for XOR problem? Okay, and you see that if you try to solve this, right? So W0 plus W1 into 0 plus W2 into 0, right? So W0 is less than 0. Then you, for next equation, you get W2 is greater than minus W0. Next, you get W1 is greater than minus W0. But the last equation, you get W1 and W2 is less than minus W0. Okay. So here is one problem, right? Because if you add the second and third, you can see it will say W1 and W2 is greater than minus W0. And the other equation is saying W1 plus W2 is greater than minus W0, right? So it was very clear that you cannot solve this problem. Okay, yeah, you cannot solve this problem, and that actually will be very surprised to know that actually took the AI community by a storm. Okay, so a lot of people thought that the AI will not have any future, and like funding almost zeroed at this point of time, which we also call as AI winters. Again, as I said, that when we talk about the journey of AI so far, okay, we'll discuss that briefly, right? So this is called as the XOR problem or XOR roadblock. Okay, and as you can see, right, so this one in blue, right, so this will have value of 1, and this ones in red will have value of 0, and you cannot possibly draw any line. So what I'm trying to tell you is that I cannot possibly try to so I can, if I try to draw a line like this, right, so I have only one over here, or I can try to draw a line like this. Again, one red here, two blue on the other side, and one red. So you cannot draw a line to actually divide this into two regions where you have red on one side and blue on another side, right? So this is what was the problem. Okay, so we started calling these problems as non-linearly separable. Okay, so we started calling these problems as non-linearly separable, and here are some examples, right? So if you have two classes here, right, so you can see that I cannot probably draw a line right? I cannot probably draw a line to separate them, right? So it will be one class, or if I try to draw something like this, it is not going to work. Similarly, this is also a very famous, two semicircle pattern, right? So I think it is called as two half moon pattern, right? So even this cannot be like these two classes. This cannot be converted into like decision regions, okay, or using a simple line. Okay, now uh, what turned out later on is, if you really want to do it, okay, then you may probably use more than one line, right? So all right, perceptrons can draw one line, one perceptron can draw one line, but who is stopping? So if I go in the extra problem and someone allows me that you draw a line over here and you draw a line over here, right? And you use two perceptrons, okay, and probably then you use another perceptron to see that whether these points are within these two lines and outside these two lines, right? So if I use multiple lines, I can solve this problem, okay. So non-linearly separable means that you cannot solve using probably one line, and here you can probably go and use a line like this, right, which is typically the radial kernel of a subvector machine, okay. So you can differentiate these classes, right, and that goes here also, okay. So essentially, yeah, and okay, so you can say that, okay, how you can get this line, right? So I don't need to get this circle. What I need to do is I can linearly approximate it. So I can have something like this, right? Something like this, okay. I'm just trying to give you the concept, so please bear with my bad drawing, right? So I can have a lot of small lines, okay, and they can give me the decision boundary. That's the idea, okay. All right, so this was the multi-layer perceptron, okay, and all right. So now, what does non-linearly separable mean in simple human terms? Can any one of you tell me? This is also a question, and I just want to see that if you are with me. Anyone wants to, I mean, you want to give some example? So when we cannot, so when the like world is not dictamous, okay, so it is not completely black and white, right? So then that's where we call it as non-linearly separable. So let's say I want to have one characteristic. If I can by one characteristic like put a line between tea lovers and coffee lovers, that okay, this kind of people are tea lovers and this kind of people are coffee lovers. If it was that straightforward, then it would have been a linear problem, right? But we'll see that there will be many tea lovers who are also coffee lovers. So essentially, it will not be a linear problem to solve. Okay. Yeah. So this was my second question for the day. All right. So now, how do we define deep learning? Again, this is a very layman type definition. So you see, when I have multiple layers of perceptron, so here you see that these circles that you see, so these are individual neurons, okay, and you will have an input layer, you will have a hidden layer, and you will have an output layer, okay. So that's the basic configuration, okay. So if you have more than one hidden layer, right, then you call that as kind of a deep neural network, okay. So you may say that, okay, if we are having only two hidden layers, we'll call it deep learning. Probably, by the definition that I'm giving you, we will call it as that's a deep learning network, okay. And these individual circles that you see are essentially the perceptrons, okay. So here we are talking about 12 perceptrons, okay. Okay, so we already saw who are the furthers of AI, right? Now it turns out that we should know the furthers of deep learning also, right? So the man in the middle, Geoffrey Hinton, you might all of you must have heard his name, right? So he's a professor of University of Toronto, right? So he was working in this area of AI from 1980. And when this research was going through AI winters, right? So he was one of the persons who perceived and continued working on this area, even with limited success. Okay, and on his left and right are his disciples, right? Joshua Bengio and Jan LeCun. Okay, so together they got the Turing Award, I think, in 2018 or 19, and last year Hinton also has got the Nobel Prize along with, I think, Hopkins for their landmark work in the area of deep learning and neural networks. Okay, all right. So essentially, right, how do you learn these parameters? So that's where now we are trying to go. Okay, so basically, you have a model, okay, and you have some inputs and you have some outputs, and you will see that the output, we have put a hat over y hat. Okay, so essentially you have an actual output and a predicted output, right? So basically, we are trying to, let's say that we are trying to predict what will be the take home package of a student based on certain parameters like their CGPA, their quant score, or maybe their verbal ability score, and so on and so forth. I mean, many things, right? And they are extracurricular. Okay, some way it is numerically represented. Okay, so one thing is that you have previous year's data, right? So which constitutes your actual wise, and then you want to use that for this year. You of course do not have the actual data, right? That you call as y hat. And when you are building the system, you can actually test against those data as well, for which you have the actual data, right? So you have some actual data, and your model also gives you some output, so which is called as the predicted data, right? And essentially this y hat is a function of x and theta, right? So x is the input and theta is the parameters of the model. Okay, and so yeah, a model is represented by some parameters like theta. So if you think of the linear regression, it is the intercept and slope term. For a neural network, theta can be the number of nodes, number of layers, weights, and activation functions, right? And it can be many more. It can be the optimization function you are using, right? Or it can be the dropout strategy that you are using. Okay, so these are essentially the parameters of characteristics of a neural network. Okay, and you have something called the loss function, right? Which again takes two inputs. One is actual y and another is y hat. So essentially this loss function, okay, so when we calculate the deviation, okay, so this is a different thing. So what now we are trying to do is we are trying to minimize the loss function. We are trying to find those set of values of theta which minimizes L. Okay, so that's the grand objective of any model. Okay, be it a machine learning model, be it a deep learning model, when you are doing an induction, right? So you essentially have a model, right? So the model has some parameters, and you have some examples. So what you are trying to do is you are like teaching a student, and you are trying to see that how close it is, okay, with the answer that is there in the back of the book and the answer it is coming up with, right? So ideally, it should be completely matching, right? So that's the idea. Okay, and yes, so what we want to do is we want to find values of theta such that the loss is minimized. And here one important algorithm that comes into play is the gradient descent algorithm. Okay, so what the gradient descent algorithm does, so essentially this JW is representing the loss function and W is representing the input parameter. Okay, so what you are trying to do is you are trying to reach this place. You are trying to find this value of W, which is essentially minimizing this value of JW. And the equation that governs this algorithm is something like this, where you say that W nu equal to W minus alpha of del of Z. Okay, so what is the meaning of del of J? Del of J actually tells that for a small change in weight, how the loss function changes. So that's the idea. Okay, so I'm not going to elaborate discussion, but as you know, this gradient descent can be used for as gradient descent can be used uh, for a 2D kind of a problem. It can be also used for a 3D problem. Okay, and it turns out, you know, that gradient descent is not new. And gradient descent, I often call it as the master algorithm. Okay, so this is a concept by which, you know, if you have inputs and outputs and you know the parameters, you can find the parameters. And the most basic algorithm, right, linear regression, okay, which is represented as maybe, you know, y equal to theta 0 plus theta 1 of x, or y equal to mx plus c, you can use gradient descent to find the line. Okay, it has been used for many cases. For logistic regression you can use. So it's a master key by which you can unlock any algorithm, right? Okay, and you must have seen something called as alpha. Alpha is called as the learning rate, and learning rate actually tells you how you are going to converge, how you are going to approach the optimal solution. So one can be that you take small steps, right, and you reach the optimal solution. Another can be you can take large steps, right, and you reach the solution, right? So you can see that probably if you you make alpha very small, then you'll be very slow to reach over here. And however, if you make alpha very large, what will happen is that you may you know, you may actually pass it also. So maybe you start from here, and instead of reaching somewhere here, you actually end up reaching here because you are taking a large step, and then again you reach here and you go here. So you cannot eventually converge. Okay, so this is the effect of learning rate. And I will say that, you know, gradient descent is one of the most important algorithms, and uh, many people call that backpropagation, actually, which holds the key to multi-layer perceptron, is actually gradient descent on steroids. Okay, so this can work for multiple layers. How? Because it uses partial derivative. Okay, uh, and essentially I'll tell you very at a high level. Okay, so what essentially we do is we have something called as forward pass. So we take the inputs, we take it, you know, through different layers, right, and then we arrive at the output. Okay, and then we see that, okay, is this the desired result? So if this is not the desired result, then you have an error, right? And then you see that, so you can understand if there is an error, then what you need to do, you need to change the parameters, right? And you may you may have to change the parameter of each layer, right? So how to do that? So I'm going to see that what is the direction of the change. So for that, actually, you need to look at the derivative. That if I am changing the weight, then is the difference going up? If it is going up, then probably I need to take down the weight, right? So that's where the concept of derivative comes. And please understand that it is very easy, okay, that if I want to find the change of weight in the last layer, okay, with the change in error, right, that is easy. But when we go here, then actually it's kind of a recurrence effect, right? It is a kind of a I don't know if recurrence is the correct term, but the idea is that it is kind of a composite effect. Okay, that when I change something here, it in turn changes something here, and then it turn changes the output, right? So when you try to find out the change weight here, you actually need to use what we call as the chain rule of derivatives. Okay, fine. And many people actually like ask this question, right? That okay, neural networks are solving a lot of problem, which is fine, but what is the theoretical basis, right? Is there at all a theoretical basis behind this, right? So again, I will give you at a very high level. So universal approximation theorem is one theorem which tells that if you give any arbitrary shape function to a neural network, please pay attention. If you are giving any arbitrary shape function to a neural network, it can learn the parameters. How? So let's say this is my input output function, okay, which is marked by this red line, right? And the first step can be that I can break it down into small rectangular pieces, okay, which approximates this input output function. So you see that this was the function and we have put different rectangles, right? And then I can think, okay, so this set of this set of rectangles, right? So probably, you know, this is just a composition, right? So this is one rectangle, then I have one another, this I have here, and so on and so forth. Okay, so uh, that's one way of, you know, componentizing and trying to approach this problem. Okay, and you see that if you know, I have a input signal like this, right? And if I do just a little bit of phase shift, okay, to the other, so I may have one input, right? And then the input, I just do a phase shift here, right? And then if I subtract this one from this, I'll probably get a pulse like structure like this. Okay, so this pulse that I got very easily, right? So this can give me a shape like this, right? So this explains that why you can actually solve any arbitrary shape function that connects x to y. Okay, so that's the idea. And here is a very quick you know, difference between deep learning and machine learning. So essentially, deep learning, you use a large number of data, large amount of data. Machine learning, you have small data sets or medium sized data sets. Okay, so deep learning is very computation heavy. Machine learning is not always computation heavy, right? And even if you give raw data, deep learning can make sense out of it. But machine learning, uh, you need what you call as pre-processed data, or actually you need to do some feature engineering, right? And deep learning, as it has a lot of parameters, take much longer time to train. Machine learning can be trained in a reduced amount of time, right? And so on. And so the next point is very important, which is about explainability. So many cases, you know, you can explain easily using machine learning algorithm, right? So you may be very surprised to know that even with this upsurge of you know, deep learning and generative AI and so on and so forth, if you go to deeply regulated areas like, let's say, finance or medical or legal, right? So adoption will depend a lot on if the algorithms are making sense to the practitioner. Okay, because you know, if you use a neural net based algorithm and you reject a loan, right, RBI is going to come after you and ask you for explanation, right? And then you cannot say that, okay, this is all because my algorithm said so. Are you understanding? So you see that, you know, it depends a lot on amount of data, right? So machine learning and other learning algorithms, the performance actually tapers off after some time. Okay, however, like data and deep learning has kind of a linear scale. So as you increase data, the performance goes up, and that holds for these large language models as well. Okay, here is what I was promising for quite some time, right? So this is the AI journey, right? So you can, this is also very important. October 1950, when Alan Turing created his Turing test, where, you know, you look at the response of a program and you try to understand whether it is human generated or AI generated, right? Okay. So 1956 conference, I already told. 1962, Arthur Samuel, again one of the like 10 frontliners, right? So he developed a program which can play checkers, right? And it actually could defeat one of the top checker champions. Okay, 1966. So there was some there was a mobile robot called as Sheckley. Okay, it was the first general purpose mobile robot. Okay, and then you have this AI winter, which I was talking about, which extended for close to, you can see, 30 years, right? So I mean, there you can probably divide that, right? You can say 2 winters and so on and so forth, but this is a general idea. 97 is another landmark year where IBM developed a chess program called as Deep Blue. So these are like folklores every one of AI students know. Okay. However, actually, it was not using AI. It was a supercomputer with like a lot of brute force kind of approach. Okay. So, however, it could beat the then chess champion Gary Kasparov. Okay. And 2002, there was this was Roomba, the first mass-produced autonomous robotic vacuum cleaner. So this was one of the uh, one of the important events. Okay, 2005, Stanford team attempted to build a driverless car, right? 2010, you have this voice assistant coming in, right? So you have Siri coming in, okay? You like, which was followed up by Alexa, okay? And then 2014, where like one of the chatbots actually could pass Turing test, right? 2018, OpenAI released GPT-1, their first of their large language models. Okay, then comes GPT-3 in like June 2020, and then the moment, right, the bombshell drop in November 2022 when OpenAI released ChatGPT to the public, right? So again, I mean, these are some of it, right? So you can always say where like that program which could beat the Go champion also. So that will be also another landmark, or the performance in Jeopardy quiz program, right? But we have so limited space. And then after that, if you see, it is completely on what is happening in this large language model, right? So 2023 March, OpenAI released GPT-4. Microsoft, integrated that with Copilot. Okay, Google released Bird, which later, got converted to ChatGPT. And if you see that, these still are three are the leaders in this space of like OpenAI, Gemini, and then of course the Anthropic series where you have the Claude and all, right? And also at the same time, what was happening was that people were trying for open source model. So Meta actually came with this open source model called as Llama. Mistral was also there. Alibaba also created some models. Then of course you have DeepSeek and so on and so forth. Okay, so what I'm trying to say is that, so this has been a story of the large language models. Like last 3 years, a peers competition is going between the giants, right? Okay. All right. So let me, take a short pause and see how we are doing, and then so like we are around 1 hour and 30 minutes, right? So if you have any questions, if you have any remarks you want to discuss, we can do that. So you can use the chat box. So that actually covers two parts. Okay, uh, the neural network part, okay, and uh, the AI forward part, right? So these are the two things that I've discussed. So uh, I'll just try to quickly summarize. Uh, so I told you, different type of AI, mainly focused on inductive, deductive, symbolic, and sub-symbolic. Okay, and what is a basic definition of AI and how people connected AI with neural networks, right? So that connection, okay. And then in neural networks, we understood that, okay, it started with MP neuron and then perceptron. So perceptron has this capability of learning parameters based on the problem given, right? And then we saw multi-layer perceptron, okay, and then we saw that how it evolved into deep learning, right? So this is essentially what we have covered so far. So now we are going to go to the next two topics that I promised. Okay, one is the computer vision side, right, and another is the language AI side. Right, so both of these I am going to discuss, and probably I'll not spend a lot of time on object. I will go more to language side of it. Okay, all right. So let's proceed. So what is object recognition, or what is the fundamental task of computer vision? So so first let's understand how a computer vision fits into the field of AI, right? So if I want to build a system, right, so that should be able to see like humans see. That's the first thing. So we can use cameras, right? But not only that, we can look at a scene and make sense of it, right? So we not only need to look at the image, but we also need to understand what is going on, right? So this field of study is called as computer vision. So giving the ability of analyzing, of understanding a scene and analyzing it, right? Like humans in a computer, right? So that's called as computer vision. And one of the basic tasks of computer vision starts with object recognition, right? Because if you want to make sense, right? So let's say you are analyzing a movie scene, right? So, and maybe someone is, firing a pistol, right? So you need to first understand that, okay, there is a person, he's holding a firearm, right? And he's firing it, right? So you have to understand the objects, right? You will agree with me. And one of the basic challenges of that is, let's say I want to identify dogs, right? I want to identify whether a particular scene has a dog or not. And here's an example of that, right? So you see there are different breeds of dog, right? So in one case, you see the front face, other case, you do not see the front face, right? So here it is behind some kind of railings, right? Here it is a very, very small sized dog, okay? And here the dog is not completely visible, okay? So these are some of the problems of object recognition. It is easier said than done, okay? All right. So uh, this is one exercise I always do. So can you look at this scene, right? So and write in chat box that what do you understand by this image? What you can make out from this image? Can any one of you try, please? What do you understand of this scene? A soldier coming home. Thanks, Rahul. Anyone else? Guys, please give it a try. Okay, so Nilendu says a soldier coming home after a long time. Okay, fair enough. Anyone else? So let me not take more time. So some of the very important things that you understood is that this lady is a soldier. Okay, you understood it very easily. Okay, uh, how a computer program will do that, right? So it can identify, okay, there is a woman, it can identify there is a dog, but how it will identify that he's a soldier? Not only that, you see, so you can actually visualize a lot of things, right? That probably a lot of people has come to receive heart, and looking at the background, you may tend to think, so this looks like some kind of uh, those uh, uh, those scanner kiosk through which we walk, right? So it looks more like an airport, right? And you see that someone presented her with a flower with a bouquet of flowers which she has kept down. There is a laptop also, and then there may be some friends and family have come, and looking at like the dog's favorite person has come. Someone has unleashed the dog, so the dog has gone and greeted her, and so on and so forth. And then you can also probably visualize that, then she will be received warmly and they will head home. So all the story that we are making out, right, all this like nuanced understanding how a computer can do that. Okay, so this is the challenge of computer vision. Okay, so I just wanted to give you that perspective. And one of the fundamental works that actually inspired computer vision was by biologist, neuroscientist Hubel and Wiesel, right? So who actually studied that how an image is formed in the brain. Okay, and the most important thing that the most important thing for the community was that it happens in a hierarchical fashion. Okay, so the brain or our vision or our eye first looks at edges, okay, then simple shapes, then complex shapes, and then it turns into faces and objects, right? So this is a process which happens so immediately that we can of course perceive that, okay, when we are looking at a person, probably I'm looking at his like hands first or legs first, right? So it's not like that. Okay, so it happens so first we don't realize it, but this is how actually it happens. Okay, and that gave people the idea of what is called as convolutional neural network. Okay, so uh, basically if you want to identify whether this is a true or not, okay, so what will happen is that okay, so this was one thing that you work in a hierarchy. And then also people saw that I actually work in a very patch-like manner. So you don't process the entire scene one at a time, right? So it's like you divide the scene into multiple small squares, right? And you process them one at a time or parallelly or however it is. But you don't see the scene one at a time, once, okay, once for all, right? So this actually gave the idea of what we call as convolutional neural network. So you have an input which is a like a square image, and then you can have what we call as kernels, right? So where what you do is that you take small areas, right, and you apply the kernel there, and you try to extract the interesting part, because not all part will be similarly interesting, right? So when we are looking at the image of the soldier, right, so let's go back here. Okay, and let's say we are looking at somewhere like, I don't know, somewhere like here, right, this portion. But then I am only interested at that, okay, this is the dog's face and the soldier is patting her. Okay, so uh, we are essentially not looking at the entire thing. So that's why we probably look it like patches. We divide this in patches, okay, and then we only look at the ones that appear to be important to us. So that's what is happening over here. And then that's what I call as extracting features. And then one of the philosophy is that when something works, when some trick works, you do it multiple times, and right. So that's what that ideology is so prominent across all neural networks and generative AI. Right? So whenever some blocks works, so be it convolution and pooling layer, or be it encoder and decoder block, you keep on repeating them, so you are better at your task, right? And the interesting thing is that you here now you have a input image and you can now classify them, right? So one of the bottlenecks of machine learning was that you cannot work with what we call as unstructured data, right? So image is kind of unstructured data, but convolutional neural network, by this technique of feature extraction, looking at one part of the image at a time, right? So it can solve that puzzle. Okay, and so a little bit about ConvNet. I showed you the talked about Jan LeCun earlier. So Jan LeCun is the one who is actually the father of computer vision, probably. Okay, and the first convolutional network that was proposed by him was called as LeNet 5. Okay, so this is a diagram which is similar to what we have seen earlier. And they could, so I am talking about 1990s, so 35 years back, right? And some of the use cases was that you can probably, so there are a lot of mails that are coming, and you can use a program to actually look at uh, the pin code and understand, or zip code as they call it, and then actually sort them into different boxes. Okay. So probably you'll also have to attach a robotic arm and so on and so forth. And also that can be used for check processing. Okay. So there were some success, right? uh, okay, so yeah, invented in end of 1980s, so 1989 or so, right? Tested limited success in reading digits from an envelope, or reading digits from a checkbook, but it was not scaling or generalizing. Okay. So yeah, so Geoffrey Hinton later said of LeCun, he kind of carried the torch to the dark ages, right? So you can understand, right, that we are talking about 1989, 90, when this ConNet was being proposed, right, and it was not getting success. It actually tasted success in 2012. So you think of this, right, that to understand, right, that when we face a problem, okay, in today's world, probably we don't pursue it, right? Even if we know that our idea is good and it is not working, we just drop it. Okay. But think of these people, right? That 1990 it was invented. The first success was 2012. Okay, so 22 years they kept on doing research on this field, right? Without success. Okay, and that's why probably they were awarded with a Turing award. Okay, one of the thing was ImageNet, and you will be very surprised to know that many of the theories are actually result of competitive data science. Okay, competitive data science or competitive AI problem. So the most famous one was, of course, the Netflix movie recommendation problem. Okay, where you have kind of $1 million prize to improve Netflix movie recommendation algorithm, right? So ImageNet was one such algorithm, one such competition, where you will do visual object class competition. So it's object recognition only, right? So there were like 15,000 photographs downloaded from photo sharing site like Flickr, okay, with human created labels for 20 object categories such as person, dog, horse, sheep, car, bicycle, sofa, and so on and so forth, and potted plant. Okay. The interest to the classification part of the content were computer vision programs that could take a photograph as input without seeing the human level, and could then output for each of the 20 categories whether an object of that category was present in the image. Okay, so there can be multiple such objects, right? So that's why you need to say that whether that object is there or not, right? And you have a training set and a sacred test set. Okay, and all right. So the thing was that the programs were only focused on 20 categories, so it was not general computer vision, and data set was not large. Okay. So here is one professor called as Fei Fei Li, very, very accomplished and known name. Okay. She is attributed to WordNet. Okay. She created ImageNet also, which is like WordNet. Okay, essentially she extended this to multiple levels. Okay, multiple levels of images. Okay, and probably it extend to 1 million images, right? Or like 10 lakh 1 million images, or I don't know, probably it was more than that, 100 million images and 10 million classes and so on and so forth. Okay, so it was large scale, unthinkable at that point of time. Okay, right? So in 2010, actually, ImageNet changed the category. Yeah, so this is what I was telling. 1.2 millions of them and thousands of categories. No, not millions, right? 2010, the winner was a support vector machine-based method. Okay, with a score of 72%, top 5 accuracy. Right? What is top 5 accuracy? So essentially, you are not predicting one level; you are predicting 5 levels. Okay, 5 probable levels. Okay, and then if you get within the top 5 level, then you are accurate, something like that. Okay, so it was 72% in 2010. 2011 also SVM was the method with 74% accuracy, and then a ConNet based method came in 2012, right, which was AlexNet, and with 8 layers, 60 million parameters to 1 week of training, and resulted in 85% accuracy. So you see the jump from 74, we are 85. And as the excitement continued, big tech giants jumped in to win. Okay, about ImageNet. So this is the person by which AlexNet is there. So he's Alex, right? And it created a lot of euphoria. So people started telling, okay, now computers are better than humans at recognizing and sorting images, right? Um, here is one headline you see: Microsoft deep learning project outperforms human in image recognition. So a lot of hype and hoopla was going on, okay, about computer vision, right? And then people were thinking, so a lot of people were thinking that, are we heading towards singularity? So what is singularity? Singularity is actually the single most important event. If that occurs, then we forget about everything, right? And they were thinking that probably it will be a time when AI will overtake human beings, right? So with enormous computing power and the ability to design and upgrade this super intelligent machine could constantly grow more intelligent, right? It could turn hostile towards us and annihilate the entire species, and these kind of things were going on, okay? And then people were also thinking about that, what about mind, what about consciousness, right? So the AI programs, will they have a mind, will they have any consciousness, right? Or will they have any kind of morality, right? So these kind of discussions were going on, and I'm talking about 2015-16 time frame, okay? All right. And it turned out very quickly that the end is not so near, okay? So one of the problem was, we call it as problem of long tail, okay? So when we say problem of long tail, what we try to say is that that there are some patterns, right, which happen a lot of time. Okay, as example, if you are trying to build a automated car, right, which will interpret the scene, the traffic scene. Okay, so a red traffic light ahead is a very, very highly probable scene, and this is where the AI program will not make mistake. You see a stop sign, okay, very, very common case, right? Or you see a construction worker directing traffic ahead, fine. There is broken glass on the road ahead, fine. But then you see that your red traffic light has lasted more than 5 minutes, even though all the streets are empty. So you know that the traffic light is faulty, okay? Or you see that traffic lights are not working due to a power failure, or snow is covering the lane marking on the road. So these are not things that the AI system has seen earlier. AI system can only work. See, induction will only work if you've seen such an example, right? You cannot invent an example like probably human beings do. AI system can only work if you have seen an example like that, right? Okay, so object recognition, conclusion is object recognition is one thing, visual intelligence is another. Okay, so this is one of the challenges of AI, the long-term problem. And the second problem is you don't know what they are learning. Okay, so these are two very famous very famous experiments. Okay, so it's like you want to identify whether there is a bird or animal in the picture or not. So if you see A and B over here, right? If you see A and B over here, you will see that this has a bird, an eagle, like going for a prey, okay, and this doesn't have an animal. So actually, when people tried to investigate that how AI system is telling whether that is an animal or not, they saw that when the background is blurred, that means there is an animal. So rather than understanding the pattern of having an animal, it was learning something else. Yeah, even in this case, right? So it was trying to identify, okay, whether there is a wolf or not. Okay, and it turned out that the AI system is trying to understand whether ice or snow is in the background or not. Okay, so and as a result, when you put any other animal like maybe a husky, okay, yeah, it actually tells that that's a wolf. Okay, so because the AI system has not understood what differentiates wool from others, but it has understood that okay, one of the pattern that is going to be there is ice or snow in the background, right? So probably ice and snow in the background, and a penguin will also be classified as wolf. Okay, so this was the second problem. Okay, and now, if I try to quickly summarize the different types of neural networks, right? So, one hand you have perceptron, and then you have the feed-forward network, the typical feed-forward network, what we call as multi-layer perceptron, right? You have recurrent neural networks. So, recurrent neural networks is something which will, go next deep in our language AI session, right? Language AI portion. So recurrent neural network essentially tells that you are dealing with sequential data, right? So it is not what is going to determine what I see now, but I also need to understand that what was there previously. Okay, so that's what is a recurrent neural network, which had certain kind of problem for which we had LSTM and gated recurrent units, right? So and then you have convolutional neural network and GAN and so on and so forth. So this is a very high level idea of different type of neural networks. Okay, so let's now move to the last segment, which is language AI. Okay, and as we told that it is not only you have it is not only that you have to make sense of what is there, right? What is there around you, but you also need to understand what is being spoken to you, right? So which we call as language AI. Okay, that AI system which can understand language and like understand language and also can represent that. Okay, all right, and you see like why it has been such a sensation, right? So you see that like when internet, okay, reached like 90% of the current adoption or current subscriber level, it took around 23 years, right? And if you look at chat gpt, right, so it could do that in 3 years, right? So that what how sensationalizing this idea of chat gpt has become. Okay, all right, and just look at the frenzy. Okay, so netflix probably to reach to 100 million users took around 10 years. Okay, LinkedIn took around 7.5 years. Pinterest, Uber, Twitter, Telegram, Facebook, right? So all doing around between 5 to 10 years. Snapchat, WhatsApp, right? Even like TikTok, right? Taking like close to 1 year, and ChatGPT was there to reach within 2 months of time. Okay, so that was the second, and like the thing that probably drove people or caught people's attention is was that you have a raw AI tool at your disposal, which you can talk to, you can get answer, right? You can ask anything, right? So it's not a difficult interface. You just have a very raw interface where you can type. I mean, just think about it. So we are away from all the glories of visual systems, right? So there are so beautiful visual systems. We have a raw AI tool where we are typing like old days, and it's giving an answer, and we are so hooked by the capability or the quality of responses it is generating. Okay, all right. Okay, so before I move on, okay, here is one more question. Which one is more difficult, image or language? Can anyone try to attempt this? So I'm getting one answer as so I get some answers as yeah. So language, image, okay, message. Depends on the context. Yeah. So that's a diplomatic answer, but you need to take sides. Okay. 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 So a lot of people actually told a lot of people actually told that it is images, but little sorry to disappoint you. Language is more important, or language is more difficult to solve actually. Uh, a plain and simple thing is that images still have some structure. Okay, and language can have no structure. And uh, probably this is, I mean, you may not agree, but this, if you look at the evolution, the test, you will look at how things happen, right? So first we have the revolution of CNNs and transfer learning coming in image, and at least there was a 3-4 years lag when we could solve the natural language problem. Okay, because of its difficulty, and I will tell you why it is difficult. Okay, I'll tell you why it is difficult. Just give me some time. Oh, so one of the reason is that there can be a lot of impurity. Okay, because you can have mixed case, right? So you can have AI as in caps or AI in small. You can have abbreviation. So you have United States, or you can have USA. You can have stop words, right? Which probably do not make much sense otherwise. Okay, like the and of. You can have different variants of the same word form, right? So you can have run, you can have runs, you can have running, you can have runner, right? Or you can have punctuation and symbols. Okay, so you can have hello with multiple exclamation. Okay, or you can have a ampersand, hash, and so on and so forth. You can have typo. Okay, or you can have duplicate words. Okay, like very, very good. So it may not be duplicate even, but probably trying to emphasize. Okay, and you can have numeric noise. So you can have IDs, phone numbers, other IDs. Okay, so which are actually numeric noise, because that doesn't give you any information. So that is one thing. Okay, all right. So here is one you can pay attention, right? So if you say that, okay, I saw a girl with a bicycle, and probably you can visualize that. Okay, that indeed this must be the thing, that a girl was riding a bicycle, and you saw it. If you see I saw a bus with a telescope, right? So you can understand that you are using a telescope to see the bus, right? So there is no ambiguity in your understanding. However, if you if you are given a statement like I saw a girl with a telescope, right? So can you tell that, like, what we're trying to say over here? I saw a girl with a telescope. Right? So it's interesting because there can be multiple possibilities. Okay, so it may be that you saw the girl using a telescope, or you saw the girl who was having a telescope, right? So that's why we it is very tricky, right? Okay. Another, I don't know. Okay, so probably I have uh, received like removed one slide. So there is a very, very famous sentence. Okay, just to make you understand the complexity of language, which goes like buffalo, 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 buffalo. Okay, so the same word being repeated 8 times. Okay, and you may wonder that is it a correct English expression, English sentence? And it turns out it is. Okay, so this is a well studied sentence, which yeah, have a lot of trivia around it. Okay, and essentially buffalo is being used in three senses. The first sense is that this animal buffalo. The second sense is the city of Buffalo, okay, which is a famous city of US. And then the third sense is that, like bully, to also use the term buffalo to mean the same thing, right? So essentially it is telling that there are Buffalonian bisons, so bisons who stay in Buffalo State, whom other Buffalian bisons bully, also bully Buffalian bisons, right? So there are Buffalian bisons who are bullied by some other Buffalian bisons, but these bisons also bully some other people, right? It's a very common thing, right? Okay, and then you have something like mixed language. Okay, ajke ami khub tired, and then use a emote icon, or you mix things. So it was like I mean there was something here. Okay, ami jani tomorrow's meeting is very important, but today I really need to take some rest. Okay, so that makes language tricky. Okay, again this is an example, right? So don't get me wrong. Okay, so a woman without her man is nothing, right? So many of you will find this outrageous. Okay, and what are we saying? A woman without her man is nothing. But here is the trick of punctuation. Okay, so it can be a woman colon without her man is nothing, or a woman without her man is nothing. So punctuation is very powerful. Like once we are saying a woman without her man is nothing, and another place we are saying that man is nothing without a woman. Okay, so that's why language is tricky. Okay, and when people were trying to look at, so there are like if you talk about language tasks, there are very many language tasks. Okay, so some of them are like NER. NER means named entity recognition, right? POS, okay, which is called as part of speech tagging, and then you of course have machine translation and so on and so forth. Okay, so there were three major things. One is this language task. Second was that even more fundamentally, that how do I express or convert a word into a number, right? Because computers only understand number, right? And please understand this challenge, okay, that when we try to assign a number, right, we will try to, so let's say I have something for I am going to examples of animals, don't get me wrong, right? So if you are like looking at crow species, like let's say puma, okay, or a jaguar, or a cheetah, or a panther, right? Right, or a lynx. Okay, so when you look at this like super cats, okay, which are similar, I need some expression which distinguishes them. Okay, please understand the problem, right? So I need one way which uniquely identifies them. At the same time, it can tell you that there is some similarity between these species. That is also very important. Okay, and so this is one thing. And initially people approached with what is called as one hot encoding, or TF-IDF, which probably we'll discuss in a short while. And then another task people are interested was that how to model language. Okay, so probably you'll see a lot of overlaps happening over here, right? So when we are trying to model language, we are also learning how to represent word. And then when we have a language model, we can actually perform different language tasks. Okay, so there will be some connection, but these were the three things people are working on in NLP. If I try to categorize the type of research that was going on. Okay, so the first type of task, right? So first type of task we call as text classification. Okay, so what you want to do is you categorize a piece of text into predefined classes. So most famous example is sentiment analysis. So you have a sequence of text, you want to say it is positive, negative, or neutral, right? Or you have topic classification, you want to categorize news articles into topics, sports, politics, technology, or you have research papers, you want to identify them as survey articles, and then original contributions, and so on and so forth. Okay, and of course, I mean the age-old problem of spam detection. Okay, so this falls under the language tasks. Okay, then like task 2 is NER, that's what I was discussing. So this falls under the first category only, language tasks. Okay, that identifying and classifying entities such as people, location, dates. right? So, if you have something like Barack Obama was born in Honolulu on August 4th, 1961, so you need to identify, okay, Barack Obama is a person, Honolulu is a location, and August 4th, 1961 is a date. Okay, and it has applications in information extraction, knowledge based construction, question answering, and so on and so forth. The third type of task which I was mentioning is, right, machine translation, translating text from one language to another automatically. So this is where still a lot of efforts are required. Okay, but again, like we have tested a lot of success with transformer, which was earlier not there, right? So it can be like hola como estás, like I don't know Spanish. Okay, so which means hello, how are you? And then so this is the third type of task. Okay, uh, now, so this is what we talked about, the language task. The second one I was talking about is how to represent a word. Okay, and here what we want is we want to convert the image into a number, right? So how do we convert text to numbers? The simplest strategy is called as one-hot encoding. So the simple thing is that let's take, we have a very small dictionary, okay, which has 4 words: apple, cat, dog, and bat. Okay, so what we are going to do is we are going to represent them by kind of a binary digits or bits. Okay, so apple I will probably represent as 1 0 0 0, right? Bat I will represent as maybe 0 1 0 0. So I'm just going by alphabetical order, right? And this will be 0 0 1 0. Dog will be 0 0 0 1. Okay, so that's why it is called as one-hot encoding. So all other bits are cold because 0, only one bit is 1, that's why hot. So that's how the name is one-hot encoding. Okay, so this is one of the easiest way to convert a convert a text to number. Okay, yeah, so this is what is given there. We sort them alphabetically, we use now binary digits. So you see one thing that every word now have 4 bits in it. Why 4 bits? Because there are 4 words, right? So I hope you got the connection. Okay, now one of the problem is that there is no way, if you try to put a similarity measure and see that, okay, cat and dog are more similar than apple, right? Apple and cat, cat and dog are more similar. There is no way one-hot encoding gives that, right? So you are not only interested at converting to a number, but you are also interested at the semantics of the number, right? And the semantics is deeply influenced by the context. Okay, so the problem is so these are some of the terms that we'll hear in again and again. So when you convert, right, this word into a number, so you are using this word and converting it into a vector, you call this process as word embedding. Okay, so there are very famous researches that happened in 2013. Okay, where the algorithms are called as one-to-vec. Okay, where there were a lot of thing on converting a particular word to a vector. Okay, and naturally, it had semantics in it. And much earlier, to even one-hot encoding, the technique that we used was called as bag of words. Okay, so what is bag of words? Bag of words is that you will have you have a collection of text which we used to call as a corpus. Okay, so now also we use the term as corpus, right? And essentially you have multiple documents in the corpus. Okay, and each document will have multiple words. Okay, so when you look at an LP, you will see that we'll use the terms word, then term, token interchangeably. Okay, so basically what we are talking over here is that we'll take the documents, and we'll think that we have a bag, and each document we are just putting in the bag. So I'll put the first in the bag, then I'll put take game, put in the bag, and so on and so forth. Okay. And then what I'm going to do is I'm going to look at how many unique words are there. Okay. So these unique words will constitute my vocabulary. Okay. And now you look at this like document representation. Okay. So document one. Okay. So you have the game of life is a everlasting learning. Right, so game has come 2 times, off has come 2 times, so that's why the count is 2. So this is why we are calling as term frequency, TF. Okay, and so this is how it will represent. So this is kind of a vector representation. Okay, so you have so many elements, and then if you extend to all the documents, right? So what will happen is that probably I will have a structure like this. Okay, so where I will have one row for one document, right? So here I will have 3 documents, right? And how many columns? As many unique words are there. So this particular representation is called as term document matrix representation. Okay, so this is this was one of the ways to do that. Okay, and then people had some oppositions on this idea. They said that going by term frequency is fine, but the problem with that is that the common words will always get more importance. Okay, common words like maybe and, maybe the, right? And like one of the objectives, please understand, is whenever we are trying to convert something to number, one of our like internal motivation is to compare them. Okay, that so let's say if I look at a person, right, and I like look at their height. Okay, so I will essentially look at, oh, okay, so we have 2 people, and the first person is taller than the second person. So we want to establish kind of order. So that's in human nature. Okay, so that's something we always do. As we started started our discussion, the brain size, right? Who has the largest brain? Okay, so this is something we always do, and for that we need a framework by which we can compare things, right? So if I want to find out if document 1 and document 3 is more similar, or document 1 and document 2 is more similar, essentially what I am trying to tell is that if document 1 has similar kind of words with document 2 than document 3, then document 1 and document 2 will have more similarity score, right? But then I mean it cannot be arbitrary. Okay, so what essentially will be done is they will represent it as vector. Each document will be a vector, and then you will use cosine similarity to do that, right? And when you are doing cosine similarity, the weight against the word is important. Okay, so here is a catch. So now what can happen is that maybe 2 words they have and many times, and you say, oh, they are very similar, but they are not saying similar. You understand what I'm trying to say? So people say that rather than using directly the raw term frequency, let me discount. Let me discount with a factor called as inverse document frequency. So what is the meaning of inverse document frequency? It says that if a particular word appears in less number of documents, right, then that particular word will have more weightage. Okay, so the weightage increases with the inverse of document frequency. Okay, and you might be wondering, okay, but what is document frequency? Document frequency is, let's say you have 500 documents in the corpus. Okay, and we are concentrating on a particular word. If that particular word, here as an example, Python has come 10 times in that 500 documents, right? So that is the document frequency of Python. Again, 400 and has come in 400 documents. Okay, so if I calculate the inverse document frequency, I'll see that Python will get a weightage of 2.65 and will get a weightage of 1.09. Okay, now even if like Python would have come 3 times and would have come 7 times, if I discount, if I multiply by this inverse document frequency, you will see that Python is getting more weightage. Okay, this is just to illustrate the problem. So this was another way of converting a document to a vector. Okay, and then of course you people started thinking of what vector. But please understand one thing, even with term document frequency, so we have done a few research on that area, like that is also probably by now 10 or 12 years old. Okay, so basically when you create a term document matrix, right, so you have the documents over here. So of course the document is a vector, but you have the words also over here, right? Words also over here. So you can think the word also as a vector. So this also will give the vector for this particular word. Okay, and essentially you see that when I want to represent the word as vectors, I want to uh, have semantically meaningful representation. So what do I mean by that? So I mean is that if I give some numbers associated to apple, soccer, house, or car, you know, uh, and you can see that, okay, there are more images over here. So it will understand that, okay, a car and a cycle will be closer in the vector space, right? Or a truck and car will be more close. Similarly, like apple and banana will be closer. A football and basketball will be closer, and so on and so forth, right? Or a house and an apartment will be closer, right? Or factory will be closer. So this is the objective, that the vector representation should be such that similar words should be closer in the vector space, right? So that was one of the objectives. Okay, all right, so this was the word embedding part. Now I am going to the language model part. Okay, uh, and language model is based on probability. Okay, so the very basic idea every one of you know though. So what is the chance of picking a red ball, right? So if a box is given, so you can understand that, okay, there are probably 7 balls and 4 are red, so the probability of getting a red ball is 4 by 7, right? So you know this. So probability is a number which has a value between 0 to 1, and sum of all probability is 1. So essentially, if I try to find out probability of getting a red ball and then add it to probability of getting a blue ball, then add it to probability of getting a green ball, and then add it to probability of getting a amber colored ball, okay, then it all should add to 1. Okay, so that's the idea, right? Okay, so what is a language model, right? So language model is like a calculator, okay, and it calculates probability. Probability of what? So essentially you can think the large language model as a black box. So you see that I have put it very intelligently. The background is also black, right? So it takes an input of a text, right, and it throws a number. Okay, so it gets a number. So that number is actually the probability. The probability, what the probability indicates? The probability indicates that whether that is a valid English sentence or not. We are just confining to English. It can be extended to any other speaking language, right? So there are 3 sentences. Okay, a cat is chasing a mouse, right? So please consider there is a. Is cat mouse chasing a? A mouse is chasing a cat, right? So you have 3 probabilities, P1, P2, P3. Again, a like quick check. How many of you are with me? So which value you think should be more, P1, P2, or P3? You can put in the chat box. Which value you think should be more? Okay, so I got a response from Manish Bahugona, P1. Thank you, Manish. Sumit says P1. Okay. Deepak says P1. Thank you. I mean, it's a great motivation that, at least 2 or 3 of you are Yeah, so Dr. Jana also says P1. Uh, Shubhankar Soren also says P1. So and it gives me a lot of pleasure to see that you are at least attentive, like after 2.5 hours almost. Okay, so I could not have done that. So much congratulations to you, right? Okay, uh, yeah. So all of you are saying P1, correct? Now, what about P2 and P3? Which one should be more? Or rather, let me ask you this, that why you are saying P1 not P3? Is P3 not correct? Is there a problem with P3? Can anyone explain? Just write something, why you think that uh, P1 is greater than P3. Any one of you, please. Yes, excellent. So Manish Bahugana says this doesn't normally happens, right? So automatically we assumed, right? Automatically we imposed kind of a world order, right? That sense of world. Okay. So we are not talking about syntax, we are also talking about semantics. And you are absolutely right. Okay. All right. So you understood what is a language model. And okay, so this is just an extension of probability that you have something called as a conditional probability. Okay, so if someone says that suppose I roll a fair six-sided die behind the screen and you cannot see the result, but I tell you it's an even number. What is the probability is also a high number, either 4, 5, or 6, right? So then you know that acha. So someone tells me that I have got a even number, so it is 2, 4, 6, and now I 4 and 6 are high numbers, so the probability is actually 2 by 3, right? But if someone would have asked you what is the probability of getting a high number, then ideally it should have been half, right? So 1, 2, 3 are low numbers, 4, 5, 6 are high numbers, but someone has specified no, actually I've got an even number, so that actually changes the game. Okay, why I'm telling you this? The reason is that actually when you look at language model and it's working off the probability of sentence. So if you want to calculate the probability of a sentence, let's say I love artificial intelligence, what you are trying to find out is probability of I multiplied by probability of love given I multiplied by probability of artificial given I love. So this is becoming conditional probability, right? So probability of artificial given I love has occurred. Probability of intelligence given I love artificial has occurred, right? So that's how you do it. And then actually it turns out that this calculation is complicated. So it is simplified, and now we, instead of taking all the words, so you can think of this as the context words, right? So which actually has happened, right? So one on the right side of the uh, vertical bar, right? So we can think of probability of I multiplied by probability of love given I, probability of artificial given love, probability of intelligence given artificial. So if we do this kind of approximation, then the calculation becomes easier. Okay, and it turns out that this is what large language models also do. The transformer based large language models also do. So if you give a prompt like write an email apologizing to Sarah for the tragic gardening mishap, explain how it happened, right? So when you give this prompt, basically, okay, so language model task, you can think in two ways. One is you can you are given an input as a sentence, right? And you predict the next word, right? And if you break it down, you will see that you can also think it as finding the probability of next word. See how we have broken it down. So yes, at a high level, it is probability of getting a sentence, but how do you get the sentence? So sentence is actually culmination of words, right? So I am given a starting word. What I now need to do is I need to look at the next one, right? What I need to do now is I have got one word and the next word. Now let's go to the next, and so on and so on. That's how the loop actually works. And It terminates when probably you get a end of sentence, right? So if the large language model predicts the next word is a full stop or a period, then you know, okay, then we have reached the end. So that's kind of the idea. Okay. So this is what typically happens, that if you give to a transformer LLM, it takes this as input, these words, and then it tries to see, okay, so deer will probably have the highest probability, and then based on decoding strategy, which can be using the maximum, you can take the next word as deer. And then it goes on, like you see that this is one more example. Okay, and this we call as auto-regressive model. Why auto-regressive? Because we are doing a regression with myself, right? Okay, so it can be the robots will are seen. Okay, so R was the most probable, so you get the robots are. Now the robots are behave, learn, right? So you are taking are not, right? And then you are saying are not eating, waking, learning, right? So you are taking waking, and then uh, so it is not turning on. That's what it is trying to say, and then you generate the end of token, and that kind of ends, right? So the large language model are actually completely focused on predicting the next one. Okay, all right. And here is just a quick trivia. Okay, so this is what was earlier language models, maybe 1960s, 70s, and so on, where you have models like 1 gram, 2 gram, 3 gram, right? So they're nothing to do with our kilogram and milligram and centigram, right? So nothing to do with that. Here, gram means essentially the number of words we are using as context. So 1 gram means we are not using any context. 2 grams means we are using one word. 3 gram means it was two words as context. And then when we tried to generate based on a corpus, based on Wall Street Journal, you see the first one didn't make any sense. Months, the, my, and issue of year, not making any sense. The next one, last December, through the way to preserve the Hudson Corporation. So some places like last December, Hudson Corporation, major central planners, right? 5%. So these somehow make sense, but entire thing doesn't make sense. Okay, and if you go to the next one, they also point to 99 point. So again, they also point is fine. Then $6 billion is fine, right? Rates of interest is fine. Mexico and Brazil is also fine, right? As Mexico and Brazil are market conditions, so this is getting better, right? The last one, but believe me, now we are getting such coherent texts. Even like 2010, when you will use a generative model for text, right, where we want to use the model for generating some language, it was extremely difficult. Okay, so this was the thing. Okay, and people, as we put it, LLMs were kind of the bingo moment. Okay, so researchers discovered that training large model to predict the next word on massive text corpora can address all these core challenges. The three core challenges that we listed out. It is inherently a language model task, the last one. It generalizes well to other NLP tasks like classification, tagging, and question answering. And it learns powerful word representation in the process. Now, very important slide, probably a textual one, but very important slide. So actually, you go to any NLP engineer, NLP researcher, and you ask them that, can you explain how transformers are able to do good in question answering? Or you ask them that how they are able to do good in machine translation. Actually, they will not be able to explain, because this is something, which we saw as an emergent behavior. So that's the magic, that you train the beasts with these billions of parameters with a lot of data, and you just train them for predicting next word. Please understand, this has not earlier happened, right? That you are training a classifier for iris data set and it will work for Titanic. So I'm not even talking about transfer learning. What I'm trying to tell is that when you are trying to when you are giving it a lot of data, a lot of words, it is learning some fundamental patterns. Okay, some fundamental patterns, and now Earlier, what we used to do, please understand this, that if we have to do sentiment analysis, probably we'll collect some data, right? And then we'll use someone to label it. Then we'll use some kind of word representation. That can be term document metrics, that can be one hot, or that can be topic models or whatever, right? Different ways to embed that. And then I'll get a matrix. I'll split into training and test set. I'll use a classifier and I'll train my model. That can be support vector machine, that can be logistic regression, and then I will check my accuracy in the testing set. So that's how we typically do an LLP task. However, now things have been just plug and play. Okay, so you give a sentence, right, and ask ChatGPT to say, tell me whether it is positive, negative, or neutral, right? So you don't need any training, any data set, nothing. So what we call this a zero shot learning. Okay, now there are a lot of things that have happened after zero shot, because of many issues. Then we have moved to agents, we have moved to agentic, we have framework. Probably that will be like too beyond the scope of the class. Okay, but this is what happened, and this is just continuation of how it can generate the email. So it starts with dear. Now you see that dear has gone here as an input, like the other example where we are talking about robots. Okay, and it can predict the next word as Sarah. Okay, so this is how it works. Right. Now, here is just a quick representation of, so we understand language model, right? Then we started talking about this term called as, started talking about this term called as LLM. Just a second. Okay, sorry about the interruption. All right, so how large is large? This is the question, right? So you look at the number of parameters, so how it has grown. GPT-2, we had 10 to the power 9 parameters, right? Then BART T5, BART, the base BART has quite a less parameters, like 10 to the power 8. Then BART GPT-3 has 10 to the power 10, 10 to the power 11, right? GPT-4 has 10 to the power 12, and I'm like GPT-5 now is it's an ocean if you just compare the number of parameters. Okay, so and just think of this scale, right? So linear regression models that we have done, multiple linear regression, right? 3 parameters, 3 input variables. We had 4 parameters, right? And now we are talking about 10 to the power some parameters, right? So this is one way why we call them as large language model. And the other reason we call it as a large language model is the amount of tokens it has used. Okay, amount of tokens it has used to learn, right? So you see that now also if you measure in terms of tokens, that is also 10 to the power 10 scales to start with. Okay, now it has been surpassed, and if you look at the training time, okay, so probably if you are just using 100 GPUs, right? So GPT 3.4 Turbo would have taken 3.7 months. Gemini 1.5 Pro would have taken 40.6 years. And when I'm talking about one GPU, so these GPUs will like cost crores of money, right? Crores of rupees, okay? And even 100 GPUs they are not using; they are using multiple of them, right? So it's a factory, massive behemoth data center that is there. Okay, and I will also talk about one particular site called as LM Arena, where you can go and find out that which LLMs are ranking how on different tasks. So if it is coding, if it is reasoning, it is creative writing, instruction following, which one is doing good. So don't get overwhelmed or carried away by this representation. This is a very old one, maybe like 6 months or 8 months back right? I have taken where Gemini 2.4 were having a clear advantage. Okay. And then, this is again at a very high level, okay, that when you try to build a LLM, what essentially you are doing, okay? So basically, the first step is that you have something called as pre-trained model. Okay, so you get a lot of data from internet and Wikipedia and research articles, and you just train the LLM to predict the next word. So what you got is called as a pre-trained model, right? And then you actually can fine tune. So fine tune can be for specific tasks. So it can be classification, it can be summarization, it can be translation, or it can be for a particular domain also. So you want to specialize for legal, you can do that. Okay. So this step is called as fine tuning, and then you also have something called as alignment. So essentially, you want to align it to people's expectations. So basically, it should not give toxic answer. It should not hallucinate. So those kind of things you do. So that's the alignment process. Okay, which you do through this reinforcement learning approaches like PPO and so on and so forth. Okay. Uh, Essentially, you will have a base LLM, and then you will fine tune, and then you will get a fine tuned LLM, and then you can give query and response. So even like when you move to like practically implementing it. So let's say I want to use a chatbot for MAKAUT, right? So and I am asking that, okay, how many what is the intake capacity of computer science? Now here the problem is that how it will understand that from where to get this data, right? So it can take from somewhere, and it can see. Please understand that its basic purpose was not to give factual answer. Its basic purpose was just to predict the next word. Please understand this. Okay. So basically, what can happen is that it can. So one funny example can be that if you ask what is the intake capacity of MAKAUT, it can give you things like what is the intake capacity of Jadavpur University, what is the intake capacity of Calcutta University, and so on and so forth. That is also possible because it may understand that you may ask similar kind of questions. Okay. So this is one problem. So that's why we told that it will be solved using alignment. The second set of problem is that where to get this data, right? Because if it starts from website, it may give you wrong answer. Okay. So what we can do is we can actually confine it using retrieval augmented generation. So basically, you can have a corpus. At corpus, you can put in a vector database. So when a query is being asked, so first, it will check in the vector database. So it will match the similarity of question with the vector database. So what is a vector database? Vector database is a specialized kind of database which stores a document as a vector. Please understand this. So not as one vector. So it takes the document, it chunks it. Every chunk it assigns a vector and so on and so forth. Okay. And then when we compare, we get a context out of this vector database. We use the question and context and we answer. Right. So this is what is typically done. Right. And then when you want to go to agents, so you need to give more access, right? So basically, the concept of agent is that I can ask ChatGPT that, okay, what is a good flight from, let's say, Calgary to Delhi, right? So the answer, I will not be satisfied with the answer. I actually want it to go one step ahead and compare different flight costs, which is fine. So it will use some tools, and then it will actually book the ticket also. So that will also need tool, and maybe it will use its memory to understand that, okay, this guy actually is a non-vegetarian. So if I have to add a meal, it better be non-vegetarian, something of that sort, right? So that makes agents action oriented. So you have memory and tools, which I explained. Planning is now being called as the orchestration, because orchestration actually tells you where to stop, where to go to user, right? Where you may need an intervention from human. So like one of the lectures I was doing just 10-15 days back, it was on agentic design patterns, right? So one of the agentic design patterns is human in loop. So you are given autonomy to an agent to execute, but it knows that okay, where it should escalate and get human opinion there. Okay. uh, all right. So uh, one more question: which part of intelligence still seems unreachable for machine? So this is a question I get from many quarters, many workshop. So basically, whatever is getting generated, right? uh, can the machine think? No, it cannot think. It is not self-aware. It doesn't understand what it is generating. You can make it, like make it evaluate it, right? But it will only evaluate from the sense of world that you have given it, from the corpora that has been given to it, right? So it is not actual thinking. It is a simulated thinking. It is a simulated consciousness. It's a simulated ethical way, or simulated morality. Okay. So I think that like brings us to close to this session. Yeah. So I end with one of the famous quotes. So we were talking about models all along. So George Box, a famous mathematician, by whose name you have this box plot, right? So essentially all models are wrong, but some are useful. So he says this because you are always doing some kind of assumption, some kind of abstraction, right? So abstraction is close to reality, but not reality. Okay. So with that, thank you so much for patiently hearing. 3 hours is a very tiring kind of. Oh, okay. So someone said the slide is not changing. I'm really sorry about that. So let me quickly share it. Thanks for telling that, but I'm really sorry. I saw it later. Just give me a second. I'll just quickly run you through the slides. I'm not going to explain. Okay. So at least you understand what I'm talking about. Okay. Yeah. Yes. So this is what I was showing. Probably after this, the slide was not changing, right? So these are the figures. Okay. The LLM competition that I was talking about, right? Training of LLM, the different phases that I discussed, fine tuning, LLMs plus RAGs and agents. And yeah, so this is the question and that quote of thank you. Okay, so thank you so much. And now if you have any questions, you feel free to ask me. And if Pritimoy is there, I will hand over to him.
Yeah, thank you, Saptarshi. So if you have a question, please raise your hand because time close to 10 now. So we have to conclude the session. So better if you have a question, raise your hand. If not, then we will conclude the session. Okay, so thank you, Saptarshida. I think
Yeah,
that you have
thank you.
actually, yeah. So participants actually enjoyed the discussion on AI. And I also again, thanks to Dr. Goswami for explaining the complex topic in such a beautiful way. I would like to thank the participants today because today is a Valentine's Day. Saptarshida already actually, yeah. So at the beginning, Saptarshida told that. And you have to listen patiently for these 3 long hours. Again, I tell you that the recording of this lecture actually will be available on our YouTube channel and the synopsis also. The next section, next lecture will be on drone technology, the interesting topic. Next Monday, that means 16th February at 5 p.m. So now I actually conclude the session in the session today. Thank you all.
Thank
Good
you.
night.
Thank you, everyone. Good night. Good night.